Just to get started, I'm excited for this session. My name's Carter. I'm co-founder and CEO of Cameo, which is a member of the solutions member of the Embedded Vision Alliance. And I've been looking forward to Neil's talk because he's going to give us a survey of all of the optimization and toolkit stuff for inference. And Neil is at NVIDIA, but is president of Khronos. And he's going to take us through a survey that I think will be valuable, and we'll have time for some questions at the end too. So just either queue them up, and we'll try to leave enough time at the end to take some. But welcome, Neil.
Thank you, Carter, and good morning, everyone. So we're going to spend the next 25 minutes looking at the most often used tools, SDKs, APIs, and try to create a roadmap for ourselves, how these all fit together. And we're going to start with a typical flow through the processes everyone follows to deploy a vision or inferencing app. And we're going to use this flow as an agenda for the next 25 minutes presentation. So anyone who's deploying deep learning needs to start with training their networks using training data. Once you have trained networks, you need to deploy it on your target or embedded device. So you need to take your trained network over into your runtime system. There are two main ways that people are actually accelerating inferencing for machine learning right now. One is compilers, where you take a network description and compile it directly into executable code, which is linked into your application. Or many people have an inferencing engine, a pre-written engine that understands how to ingest a neural network description that can be linked into your application too. Often, there's a mix of inferencing and vision, so a vision library might be involved, and all of those pieces of runtime software need to typically access hardware acceleration. That's really the point of this talk. How do we get that layer of software to effectively link into and use hardware acceleration, both for inferencing and for vision processing? So that's our goal. Let's start at the top and work down. Training neural networks. Training neural networks typically is much more intensive computationally than inferencing. You typically need 32-bit floating point to get good convergence on your training sets. And I'm sure everyone here knows this is a super active, interesting area. It's very easy to create a PowerPoint slide with this with over a dozen training frameworks. They're evolving and changing all of the time. It's super to see so much innovation and investment into how we train our networks. Because it's computationally intensive, these training typically happens on high-powered desktop machines or the cloud, typically using either GPUs from any of the main vendors or TPUs. If you're using GPUs, there's a lot of well-established GPU APIs. NVIDIA has CUDA, there's AMD, has the ROCm stack, OpenCL, SYCL, driving down into very optimized compute libraries like QDNN, CLDNN, which is the OpenCL version, or MIOpen. So that is the training end. This is the Embedded Vision Conference. So we're going to focus mainly on how we take those trained networks. Now, how do you get your trained networks over into your embedded system? We've already seen there's dozens of training frameworks. There are more than dozens of embedded processors and engines. So having every engine being able to understand every output format from every training framework, that's a lot of busy work. And so it's not surprising that there's a couple of transfer format initiatives in the industry. So that's NNEF and ONNX. Let's take a look at those two and see how they compare. The idea is that you can get your training framework to export a standardized exchange format for your trained network, and it makes it easy for your hardware vendors. They don't have to import dozens of formats. They can import one or two. ONNX and NNEF, they're actually technically quite similar, but they're coming from different perspectives in the industry. ONNX has a lot of momentum in the industry. It's initiated by Facebook and Microsoft. It's an open source project, and it's pretty awesome because it's moving very fast to track all of the innovations in the training and authoring framework space. NNEF has a slightly different perspective. It's coming from Khronos, which has a more of a hardware acceleration angle, and it is primarily focused at taking your trained networks into your hardware inferencing engines. So it has a governance model, perhaps is well suited to that. All of the hardware companies have a voice and a vote in how NNEF develops, and it can develop at a pace and in a way that is most suitable for the hardware community to ingest into their engines. But both are good, and I think you're going to see, in fact you will see any moment now, that you can transfer trained networks between the two frameworks. So I think ONNX currently has more industry traction. NNEF, though, I think will gain more as hardware inferencing begins to spread pervasively through the industry. One interesting angle is the fast-moving open source project like ONNX is awesome for the authoring framework, which is a fast-moving field. In the embedded space, particularly if you're developing safety-critical hardware, perhaps for automotive or avionics, you don't want to have your framework changing too rapidly, and so the more considered roadmap for NNEF might be a better suited to what you're trying to achieve. NNEF is a Khronos standard. We're working hard to increase the software ecosystem around NNEF. We have now, since the last EVS, we've released translators for Caffe 2, TensorFlow, TensorFlow Lite. We do have a bidirectional converter to ONNX, so you can go between the two. We have syntax parsers and validators, and we've just put up a model zoo, and we're going to be soon launching a conformance program so you can test whether your inferencing engine is properly processing the model zoo trained networks that we'll be making available. And all of this is in open source. Okay, so we have our networks. Let's bring them down into our target device. So the first method I mentioned is direct compilation. This is another super interesting field, a lot of research and investment going on to figure out how to take a trained network description and directly generate executable code. It's interesting that all of the key cloud platforms have strong investments in this field. Amazon with TVM, Google with XLA, Facebook with Glow. Also, Intel has been sponsoring a very interesting project, PladML. All of these projects have a similar goal. Take your network description and generate executable code. So let's look to see how that happens. This is an overview, so this is at a very high level. But you can see, once you zoom out a little, they all are consistently doing the same three basic steps. They're not necessarily trivial, but they're all doing this, following the same basic process. They have the import of the network description. It can be one of the proprietary formats, or it may be one of the non-proprietary exchange formats. And then the interesting step is step number 2, where you take that network description and you have a holistic description of the complete neural network. So that's really the power of this approach, is that you have all the information that you need to do holistic optimizations on how that graph is described and how it's going to be executed. And many of these projects have quite sophisticated compiler optimization stages that are applying optimizations such as node fusion, bringing multiple nodes in your neural network graph together so they can be executed as one node, which can be a lot more efficient, or using more hardware-oriented optimization techniques such as memory tiling to try to keep as much of your computation in cache as possible. And then the last step is to emit executable code. And it's interesting, you're looking across the various frameworks, you're not typically generating machine code. You're typically coming down to either an intermediate representation like LLVM, if you want to take that code and then compile it for your CPU, or one of the accelerator APIs. The accelerator APIs are becoming a compiler target increasingly in this inferencing space. And we'll see in a moment, OpenCL is typically the non-proprietary target API for offloaded acceleration into heterogeneous hardware. We'll come to that later. So there's been a lot of debate. We just came from a Khronos face-to-face meeting, a lot of debate around how advanced is this, how much progress are we making? Is this the way to do it, or are the inferencing engines always going to be more efficient because you can hand code them? There's no decision yet. But the consensus I'm sensing is that over the next few years, I think these compilers are going to make significant progress in generating efficient code. But we still do have a number of years to go, 5 years perhaps, before you always beat the inferencing engines. And it's going to be a super interesting discussion to see what the accelerator APIs need to provide to these compilers to be an effective target. Potentially, if the compilers continue to advance as quickly as they are, the underlying APIs can actually remain pretty simple and just provide pretty atomic operations, perhaps on matrices and vectors and tensors. And we don't need to put a lot of baroque machinery into the underlying acceleration APIs. We'll see how that works out. It's going to be very interesting to watch over the next year or two. It's worth noting, too, that a couple of notable embedded hardware vendors are beginning to invest in their compiler chains. Siva and Cadence both have compiler-based approaches to their inferencing stacks. Okay, so what are the compilers competing against? What are the inferencing engines that are out there? The answer is, there's a lot. This is exactly the same slide as I showed last year. The PC and mobile platform vendors have defined their own stacks based around inferencing engines. They all follow the same 3 basic steps. They import a file format. Again, it can be a proprietary format or it can be an exchange format. They have an inferencing engine. Apple has CoreML. Google has NNAPI. And Windows has WinML runtimes. And they all, because these platforms all have GPUs, they all run accelerated on top of a classic GPU API. Windows uses DirectX 12, Apple uses Metal, and Google uses OpenCL ES, and they're transitioning to Vulkan. But you can actually zoom out further. So those 3 inferencing engine stacks are at the top there for Google, Apple, and Microsoft. The next layer down is that the GPU vendors on the desktop are creating inferencing engine solutions. For example, Intel has OpenVINO, which is an excellent mix of inferencing and vision processing accelerated on CPUs and GPUs. NVIDIA has TensorRT, which is an inferencing engine that runs over cuDNN and CUDA. The interesting space, though, I think, and again, because this is the Embedded Vision Conference, are embedded inferencing engines. Increasingly, the mobile and embedded hardware vendors are beginning to ship their own inferencing engine solutions. ARM, Huawei, Qualcomm, Synopsys, TI, VeriSilicon, they all have inferencing solutions and engines of various shapes and sizes that are beginning to ship today into the marketplace. Interestingly, and again, we'll come on to OpenCL later, the interesting common denominator, and this was actually a surprise even to the OpenCL working group, was they're all using OpenCL as the underlying acceleration API for offload from the CPU to accelerator hardware. So again, it's awesome to see so much innovation and investment in this space. But a valid question is, wait, these are all proprietary. What happens if I care about cross-platform inferencing? Are there any cross-platform, non-proprietary engines and solutions out there? The two most obvious ones are OpenCV and OpenVX. Both had their origins as being a traditional imaging library or API, but increasingly both are becoming fully integrated into the inferencing stack as well. Let's quickly look at both of those. So OpenVX is a Khronos API, and it's been shipping for a number of years now. It's quite well established in the industry. The key concept behind OpenVX is you describe your vision processing operations as a series of nodes or Lego blocks, and you clip these Lego blocks together to create a graph description of your vision processing that you want to execute, and the silicon vendor will then take that graph description and optimize it to run on their hardware. It's at a high level of abstraction, so you can run it on pretty much any class of hardware that you wish. So you get good code portability across different vendors' processors. Increasingly, OpenVX has been extending itself to include inferencing. Now you can include deep learning CNN nodes as part of the OpenVX graph itself. And we're working on a direct NNEF importer. So this means your graph now includes both your vision and your inferencing nodes, and you can undertake holistic optimizations across all of the vision and inferencing processing steps that you want in your application. And there's a presentation coming up this afternoon. A lot of vendors are now reporting that they're getting good performance from OpenVX that is comparable to hand-optimized code with significantly reduced effort. OpenVX is very complementary to OpenCV. OpenCV is an awesome open source project, a magnificent resource for the industry. And again, just like NNEF and ONNX, different perspectives, I think, make them complementary. Where OpenVX is an API designed to be implemented and shipped by hardware vendors, OpenCV is a huge open source library with a lot of awesome functionality that people can use as they wish in their applications. It's actually interesting to see the functionality of the two kind of converging. In OpenCV 3, they had the transparent API or TAPI that lets you offload OpenCL functions to OpenCL devices. And now the latest OpenCV 4 has a graph API model. So graph descriptions come to OpenCV, again, to enable better optimizations holistically. Also, OpenCV now has a deep neural network module that lets you construct the neural network graph and execute inferencing. So the two are kind of converging. I think it's good confirmation that graph descriptions are useful, and vision and inferencing definitely belong together. And there's also an OpenCV presentation this afternoon, just after the OpenVX one, so I'm looking forward to that. So we have all these compiled codes, inferencing engines, application code, vision libraries. How do they take the final step and get down into the hardware? At the highest level, I think you can categorize the accelerator APIs into two. There's the GPU APIs, and there's the heterogeneous API. In the GPU space, very active area, being driven largely by gaming and interactive applications, but increasingly the GPU APIs are getting more and more sophisticated. Compute, better support for small data types, such as 8-bit integers, that typically haven't been so well supported in GPU APIs, which makes them more effective at vision and inferencing operations. But what we're finding is people are realizing the end of Moore's law is here. People want to leverage heterogeneous hardware. They want to use GPUs often, but they want to use multi-core CPUs. They want to use FPGAs, DSPs, dedicated hardware. There's only one framework in the industry that lets you program that diversity of heterogeneous hardware, and that is OpenCL. And I think that's why we're seeing, in the last 6 months, we've seen a real uptick in interest in OpenCL. Before I go to OpenCL, though, I want to just make one observation on the GPU APIs. Safety critical. The safety critical space, which may be relevant to some of you here, has had a long-term need for GPU APIs that can be easily safety certified. This started with OpenGL SC back over 10 years ago for avionics displays, OpenGL SC2 just a couple of years ago for automotive displays. But now there's a really strong demand for a generalized compute and graphics API for this new generation of smart devices. We've just established the Vulkan Safety Critical Working Group inside Khronos that's looking to see how we can take the newest generation GPU API, which is Vulkan, and create a safety critical version, a version that you can integrate into a system and have an easier, less expensive time achieving system level certification. This demand is mainly coming from the automotive space, so ISO 26262 is key. Vulkan is potentially quite a compelling place to start. It's already quite a small API. So the working group is looking to see how we can further reduce the surface area of the API, make sure that all the behavior of the API is deterministic, and we have things like robust error handling and compliance to MISRA C. This is just started, and of course anyone is welcome to join and participate. But let's look at OpenCL. I think we're finishing up with OpenCL. OpenCL is pretty pervasive in the industry for some of the reasons I've already mentioned. A lot of hardware vendors are shipping OpenCL. A lot of desktop apps use OpenCL. There are computation libraries. There are linear algebra libraries, math and physics libraries that are shipping. And of course, for the vision community, we have things like OpenCV, OpenVX, and Halide. All have OpenCL accelerator backends. But again, the interesting thing that's the trend that's appearing over the last few months is all these compilers and inferencing engines for deep learning applications all have OpenCL, the choice of OpenCL accelerator backends. In many cases, these inferencing engines have multiple backends. It's not always just OpenCL, but OpenCL is the non-proprietary cross-platform solution that many of these solutions are using. I wanted to quickly mention SYCL, which is another Khronos standard that is intimately related to OpenCL. It builds on top of OpenCL, like many of these other frameworks. And it's really interesting if you want to write in standard C++, you want to write and have a single source file for your application, and you want your offload code to be automatically generated. The SYCL solution will let you use standard C++ mechanisms like templates and lambdas to indicate what parts of the code you want to be offloaded. And the SYCL compiler will take those sections of the code, put it through an OpenCL compiler to the device of your choice, whilst running the rest of the code still on your CPU using your normal host C++ compiler. And on Thursday, there's a course that includes SYCL. Again, if you have a large C++ code base like TensorFlow, you actually take the TensorFlow engine, which is written in C++, run it through SYCL, and use it as an inferencing engine, and you get pretty good offload performance. OpenCL is busy evolving. We're developing a number of extensions that will be shipping, and the ones that get industry traction will be integrated into the next core release. We're targeting OpenCL next in 2020. One of the most pertinent extensions that's being developed by Intel is extensions to enable explicit control of scratchpad memory. which will suit, I think, can be very enabling for a number of embedded type processor devices. The key thing in the core spec for OpenCL Next is what we're calling the flexible profile. The idea behind the flexible profile is to give a lot more deployment flexibility for processor vendors. Right now, OpenCL is pretty monolithic. If you either have to take all of a version of a spec, like Open 1.2 or OpenCL 2.0, all or nothing. You're either conformant or you're not. And there's stuff in OpenCL that may not be so applicable to, for example, low-level imaging devices. You have to have, for example, 32-bit floating point. So the flexible profile in OpenCL Next is beginning to slice and dice OpenCL functionality so you can just ship the functionality that's relevant to your customers and your market. That might lead to fragmentation, so we're discussing feature sets, groups of features that are targeted at specific vertical markets, such as embedded inferencing and vision processing. We're noting that some markets really care about application portability, and so feature sets will be really important to make sure that developers have a consistent platform. Whereas other vertically integrated markets may not care about application portability at all, and so we're discussing giving the flexibility to hardware vendors to literally just ship the features that they wish and nothing else, and still be conformant. This could be very enabling for, again, safety-critical markets, where you can reduce your API surface area to precisely fit your deployed system. My last slide is OpenVX and OpenCL becoming more closely entwined. OpenVX is nice because you have these Lego blocks you can clip together, but as always, what happens when the Lego blocks don't quite do everything you need? OpenVX now has custom nodes where, for example, you can write OpenCL code and have any OpenCL code you like running in an OpenVX node. And we have OpenVX, OpenCL interop. So OpenVX and OpenCL can share data and memory with all the appropriate synchronization. So OpenVX now gets the next level of flexibility using OpenCL as a foundation. So that's it. Hopefully that was useful. I would encourage everyone to join this afternoon's sessions at 1 and 1:35 on OpenCV and OpenVX. And we have a workshop on Thursday, which is going to go into a lot more depth on the Khronos APIs here. We still have a few seats left, not many. So if you're interested, please sign up for that. Thank you very much.
We may have 1 minute for any questions that are urgent. Otherwise, I'm sure you can go wheel into a conversation on the side. Does anybody have something urgent for the next session? Okay, go ahead.
So you mentioned the OpenSC.
Yeah.
Does that mean that that's the route you're looking at for compute rather than OpenCL SC?
No, I think both. One, it's not a zero-sum game. So there has been discussion around OpenCL SC as well, but actually there's less to do in OpenCL. OpenCL is already lighter weight than the typical GPU API like Vulkan. And I think, here's the way I think it's going to work out. The flexible profile, which is going to be in OpenCL Next, is going to give us 80% of what we need for an OpenGL SC. It won't necessarily be called OpenCL SC because it's going to be standard. I think we'll deliver that, and then we'll figure out what pieces are still needed by the safety-critical community, and then perhaps do an OpenCL SC version. Yeah. We're finding that if you have a GPU, the GPU APIs are cool. If you don't have a GPU or you have more heterogeneous hardware, OpenCL gives you good flexibility with slightly less complexity. Okay.
Thank you very much, Neil. That was a great guidepost there.